All right, I guess we can get started since we're already 5 past 2. All right, so we welcome today with us Carlo Vittorio Cannistraci. He's a professor in the Center for Complex Network Intelligence in the Tsinghua Laboratory for Brain Intelligence. So Carlo is going to talk about brain-inspired sparse network science for next generation efficient and sustainable AI. As usual, if you have questions, we can either take them at the end, or if you have a very urgent question, we can circulate the microphone. So please wait for the microphone. Yeah, I'll leave you the floor.
Thank you so much for inviting me here. And I want to let you know that actually I arrived in Tsinghua, in the Tsinghua Laboratory of Brain Intelligence, and was affiliated with the Department of Biomedical Engineering. And then I also am adjunct in computer science and so on. But recently, in Tsinghua, we create a new department, the Department of Psychology and Cognitive Science. There is somehow a replication of the brain and cognitive science department that you have here in MIT. And the Department of Psychology now is changing totally to go towards the new generation of AI, and therefore is becoming a department in which we have a strong AI part. And I moved in this department, and we are doing a global recruitment. Our dean is actually an MIT PhD student of the Department of Brain and Cognitive Sciences here. So we have a link already with you because our dean grew up as a PhD student. And if you want, we have also position in my postdoc position in my department. And you might wonder, I'm a physicist, what I do in a department like this one. And somehow is what I'm asking myself, because I was in Department of Physics in TU Dresden and computer science. Here I got the Young Investigator Award for Physics some years ago in 2016. But now I end up in a department in which AI is crucial for the point of view of cognitive science. So you are welcome to apply, although you are actually, if you are a physicist, even better. Our research in my center is on information theory, machine learning, and network science to investigate the physics of network, the adaptive complex system at different scales. And we have two parts, one on theory, in which we work on network geometry, on network topology, network automata as models of self-organization, complex network intelligence, brain-inspired computing, and geometrical machine learning. Then we have an applied part that is on brain networks, omic data, design of multi-omic biomarkers, neuromorphic computing, and socio-economical systems. Today, we will focus on the part that is related with the number 1.2 and 1.3, network topology and the brain-inspired computing. However, if you go on my website, you find a quote that I use it to describe what we are doing currently, is that if physics study the principle and the mechanism of the outside universe, brain science study the principle and mechanism of the inside universe. And my research is dealing with physics, engineering of complexity, and intelligence. And we are trying to study the principle of natural artificial intelligence. And part of my research is on AI for complex network systems. The other part is on the reverse, on complex network systems for AI. If you are interested also in the first part, you can refer to my literature. There are different parts, but this article is a seminal article that solved the inverse problem on how to find the way to embed a topology network, just a binary connectivity, in hyperbolic space, giving the assumption that this network has a hierarchy and a power law degree distribution is actually related with an hyperbolic geometry. So the point is, if I don't know anything about the node original position in the general space, can I solve the problem to find the location of the node to infer the geometrical distance? This was an open problem in the field of network geometry. And I solved it using AI. If you're interested, you can look at the data. Today, we will instead focus on how to go from complex network system to design AI. And this topic is quite new. I'm pushing it a lot in the field of network science and AI. And this year, we will have a satellite here in Boston at the Network Science Conference. There is the flagship conference in network science. We created for the first time this satellite on how network science informs AI. If you are interested, you can submit your abstract, you can go to oral or poster in our satellite. We are very happy to receive also topic on AI for complex network systems. We are not just rigidly looking at network systems for AI, but I hope that you can consider to look at our satellite. Now let's start to go deep in the topic. When we use the word graph and networks, we use this word often in a similar way. Me too, when I speak with colleagues, I use in a similar way. But in reality, behind the word network, there is a bit more information. This word is used more in physics. And when you speak of graph, you think to a tool to describe the combinatorial connection of between entities. When you discuss of networks, as you analyze the word, there is the first part that is net, the second one is work. When you have the word work, it means there is dynamics on the back. Even in my language, in Italian, I don't have a translation for network. I have just a translation for net. And we call it rete, or a translation for graph. There is a grapho, but not for network. This is very interesting because this word has inside the fact that there is a dynamical system on the back. It is used especially in physics. Why? Because in physics, we consider especially in the physical complex system, we consider that behind many complex systems, there is a network organization. Why? Because a complex system is that system, the function of which emerge not from the single node, the single part, but by the interaction between them. Therefore, the fact that you have the interaction is a fundamental point in the complex system to give emergency to new property. And therefore, if you look at the city map, the relationship in a network of urban connection or ecological network or social network or IT network, or even brain network, there will be the topic on which we today concentrate. You will see that all of them share similar property at different scales in network science. And these properties are fundamental to understand why these systems are able to perform tasks that emerge by the interaction of the part. And we want to understand what are these principles. Because if we understand this principle, we can understand how these are related to intelligence, adaptive system, and put inside AI. So one of my passions when I was a master student was actually the fact that the brain was efficient. The brain is able to work with less than 20 watt of power. I think that actually there is no electricity powder that enter inside the computer and shut down. Can we make sure the electricity enter in this cable, please? And then we will be fine for all the talk. We just need to make sure that the electricity enter in the cable. Okay, this one. So let's do something. Let's change the connectivity. This one should be. Okay. All done. So the passion, the fact that I had this passion for this less than 20 watt was connected with some reason. In the course, the professor of intelligent system and brain bioengineering were explaining that the brain has two important features that support this efficiency. One is the sparsity, and the other is the morphology. And then there are many others, like sparsity can be interpreted as connectivity, activation, and so on. But today, we will focus on these two, sparsity and morphology. And one of my observations as a student, because my course was a mix of physics, computer science, and bioengineering, it was that in reality, the model that I was studying in 2000, around 2000, that was the period I was a student, were absolutely fully connected, point neuron, there was no morphology. And today we know that this model, when scaled, they take gigabyte to be trained. So this, it means that if you want to train a foundational model, you need 3 or 4 gigabytes, you need 3 or 4 power plant, nuclear power plant. How come? How can we solve this problem? Why we need to continue to scale this model in a not really careful and thoughtful way? We need to find a solution to that, because the brain is able to do that with less than 20 parts. And one of the first problems for me as a master student was to work on the level of the sparsity. And my dream was to create AI that was working similar to the brain. And this was the period in around 2000, 2002. Around 2002, I had to ask also my master thesis. And I went to the professor in computer science. I asked the master thesis on sparse network. So my idea was actually to implement what we studied in the course of bioengineering is called dynamic turnover, synaptic turnover. It means that during the training in the brain, some synapses connectivity disappears, some connectivity appears. And during the evolution, the brain cut what is not useful, add what is useful. I wish to emulate this in the brain. And my idea was to study dynamically sparse models. And on the other side, I had many questions. So what is the computational advantage of this dynamic connectivity sparsity in brain biology? How to make profit of this at the level of artificial neural network? And this was under the name of topology for me, of how the local connectivity make the difference during the evolution. And then there was the problem of morphology. So the dendrites are fundamental in the processing, and the signal can go from in one direction on the other direction. This changed at the level of the soma, the integration of the signal. All of this at the level of paradigm was neglected in the way the neural network was created. So there was a lot to dream, a lot to design, a lot to imagine as a student. And proposing the first topic was for sure the first thing I would do. The third one is the neuroglia. The fact that in reality, in the brain, you don't have only neuron in glia, there are other cells. They do meta learning, they learn on top of the neuron, and they learn how the neuron learn to know them. Fascinating. But no, nothing of this was implemented. So let's start from the sparse connectivity. I thought I started to try to do this when I will ask a master thesis on this topic. And I submitted to different professors this idea proposal, and all of them told me, no way, this is not interesting, neural network don't work. We use sparse, it was the period of 2002, the dark age of neural network. And the professor told me, no, we want to do, you do a thesis on a large margin classifier, subtor vector machine, LAS, logistic regression, whatever is a statistical machine. But I was not interested because my dream was again to go in this direction. So I decided to take a thesis to study myself. I read this article on Lascio Barabbaso in 1999. It was just a few years before. And I started to understand that I should study network science because I should learn how to model sparsity. If you want to, you want to do a dynamic sparsity in neural network, you need to know how to model it. So I wanted to start from the basic, how to learn the principle of networks. And I took a thesis on the network biology, because in the field of network biology, they were more advanced than in network neuroscience. They didn't exist. And therefore, in network biology, I could already see applied to many interesting paradigms of adaptivity in biological system, how the network play a role, and learn the basic tool, mathematical and computational, to model the sparsity in biology. So I started, I take a master thesis in network biology, and then I continue to think myself about this concept of a free research by myself on the brain sparsity. And I was astonished by the fact that the quote of Donald Webb, the neuron that fire together, wire together, was interpreted actually by the computer scientist only one way, practically giving a network that is static and generally fully connected, how to change the weight. And in reality, Donald Webb never mean that you need to change the weight on a network that is fully connected. he instead pointed out that they wire together. So in my opinion, there was room to do another part of research in which we investigated the mechanism on how in sparse artificial neural network, the connectivity arise because of the local factor. And this is clear because in reality is an ensemble of neurons that fire together, wire together. How to detect this ensemble of neurons that fire together by looking at the connectivity already, analyzing it. This can suggest where the new link should come. So I created something that I call myself epitopological learning. That it means the definition on how in brain, but in general in complex system they use network, the new topology emerge as an evolution of the topology at the stage before, because of the memory trace that the dynamic live in the connectivity. Practically, the connectivity already tell you where the next connectivity will come, because it's shaped with a preferential type of geometry on the back. So in general, when I discuss a complex network intelligence, it means how network connectivity influence the function in complex system, and in particular learning intelligence. So how the network can learn by changing the connectivity, how the different connectivity during the evolution change the process of that. These are the questions behind them. And then I realized that this topic in network science was formalized as a problem of link prediction, giving a network in a certain time t with a certain connectivity. Am I able to predict just looking at the connectivity at the link that will emerge in the future? This is link prediction. Giving a protein interaction network for which I don't know some protein interaction. Can I predict the missing interaction and use them in my modeling of protein interaction network by looking at the knowledge there in that moment? And all these problems were characterized by the concept of link prediction in complex network. And then I reviewed the literature, and Mark Newman, a famous physicist from Santa Fe Institute, in 2000, always that period, 2000 is the period in which network science, modern network science emerged, proposed a paradigm. This paradigm is very simple, and there were different articles in which they gave evidence that works better than any other complicated method to predict the likelihood that two nodes interact. In social network and other type of is the paradigm of common neighbors. Mark Newman was explaining to the community, colleagues, if you look at social network, the likelihood that the interaction emerge between two people is proportional to the number of common neighbors you have. Practically, you need to have a certain mass. The higher is the number of common neighbors, the higher is the likelihood that these two friends will be, with these no friends will be introduced to each other because they have many common friends. I was shocked because behind this, I saw somehow an echo of what Ebb was telling. And my intuition was that Ebb in reality found a principle looking just at brain network. There is in reality a principle in general, any complex network that is based on local community. So my intuition was, oh my God, but you want to see the Ebb find a general principle how system learn, but he identified in brain network. He was a psychologist, imagine, not even a quantitative scientist. So how great is it? And then I thought, how to make sense of this principle under the lens of Ebbian theory? Well, my idea was that you should look at how the common neighbors interact to make sense if they create an ensemble of neurons that fire together. Because in order to fire together, these neurons need to minimize the external link because they need to create a local community. And if you don't have the minimization of link to all the other part of the network, this is not anymore a functional module that do a local processing, like it can be an ensemble of protein that do a protein complex, or an ensemble of neuron in the brain that do a neural circuit. They need isolation, an energy barrier, the physicists would call it. Okay? And on the other side, you need to take in consideration, in some cases, also the the internal link. But the necessary condition is to have a minimization external links. I put down, so the story is very long. I don't enter in detail all the publication I made, but now I boil down to the main principle. Okay, otherwise I should show how this work on connectome of the brain. I can predict much better than previous method. I modified all the method based on common neighbors. I put inside this idea and show that we perform 1,000 better in link prediction in comparison to classical method. But all of that I neglect to go to the point. The point is that after some years, I arrived to a very simple formula. The formula says that to compute the likelihood that two proteins interact, or two neurons interact, or two people in the society interact, and so on and so on, you need to count the number of common neighbors, penalizing for the number of external links. The formula is very simple. It's the sum of path 2 in this case, but you can go also on path 3 or on path 10. Depends how you define your neighborhood, or of the number of common neighbors. The number of common neighbors give you a critical mass, but the minimization external links, they tell you the existence of the local component. If you have a node that connects to all the network, it doesn't have any meaning for the local function. But if the node minimizes the external links, then it has a role in your local function. Okay? And this minimization changes the performance drastically in comparison to common neighbors. Okay, it's a really important point. And this was verified by Lascio Barabasi, the same author that wrote the science article that I will now visit here in Boston on Monday to give a talk. In 2019, they arrived at the conclusion that in prediction of pro-interaction, one of the best method on 23 different method tests, on many pro-interaction was a method I invented with this thing. Then Tao Zhou, independent study on 2-step or 3-step based method. The story of 2 or 3 steps I can discuss with you separately, but practically the idea is that there are systems that work in a similarity way, social network, systems that work in a synergistic way, protein network. 2 proteins are similar, don't interact easily. They tend to interact by protein, they are complementary. Okay? So this is another part of a physical composition I should touch, but I don't have too much time. We can speak on the side. But independently, they define systems that are on 2 or 3 steps in more than 100 network of different domains. The Cannistraci perform the best. And then now there is a large literature that shows that this modeling perform the best. It's very simple, just a simple equation. Better than machine learning, better graph neural network, better than other. And now, if you go in this new RIPS 2025, we published an article on how, giving any network, we can predict with the right rule based on path 2 or path 3 the connectivity, but we can also tell you back the type of process, nonlinear process that happen on this network. Explain it, okay? And this is the first time that in network science you can arrive to experimental model that can predict at this level. Here we test more than 1,200 network on any type of domain of science. We show that we perform better the graph neural network, better than most advanced message passing method based. We show that modifying this method on path 2 and path 3, they perform better, validating also the graph neural network should be modeled on path 2 and path 3, and so on. And this is more or less a main figure that show how work this adaptive machine. And I don't want to comment on this one because I want to go back now to the main questions of 2000. So after years in which I tried to find a golden rule. I didn't find a golden rule, but I found a bronze rule at least. Okay, it is there. My dream was to return back on my thesis, master thesis idea, and to plug in the artificial neural network and to show that we can perform better than densely connected. And we are more efficient. Now, in the meantime, also in computer science, they started to develop a model with, these are now all the estimation, model with a lot of parameters, and they start to understand that they should go on sparse AI. And there are now also rising of money for companies, they do sparse chip, and so on, but we are late. We are too late because implementing a sparse chip is not really simple, okay? But in the meantime, in 2018, once I was in my last year into Dresden, waiting to move to Tsinghua, this article came out. Scalable training of artificial neural network with adaptive sparse connectivity inspired by network science. Done, I thought. They understood everything. I don't need to add. They catch the idea I had, probably. The other people start to think to me. Because the title is perfectly my project for my master thesis 20 years ago. But pay attention. What they did in this article, I am dyslexic, I have some problem in reading, I compensated, I can read, but I was able to read all the article in 40 minutes, so for me it's a record. In a coffee in Dresden, I just open and start to read on the phone, and looking for understanding if they catch my idea. Unfortunately, this didn't happen, because the idea of dynamic sparse training is to start sparse, so you don't start dense and put a loss on a penalization L1 or 2 or whatever you want on the loss. You start sparse. Then you organize the topology at the beginning with a modeling on network science, the user does training. Then you train and you learn some weights. Then you remove the weights with the lowest weight, okay? And once you move, let's say, 3% of the link you have with the lowest weight, you need to decide how to add. And that was my research for 20 years. There is law, fixed on finding a general rule, it was that one. So let's see how they did it. Any idea of what they could do now? What you would do if you don't have a rule? Yeah, indeed. Random. So random grow. Random grow. And the point is that if you grow at random, the real process of evolution is on the selection. Here, when you remove, because here you just equally connect. So you hope that after many epochs, by removing and equally connecting after, you find some conformation they are better and continues to grow. But as you understand, the topic started to be hot, and Google arrived in 2020. They proposed this article, Rigging the Lottery, RIGL, and the idea is to use the gradient to grow the new link. You look at the gradient of the missing links, but this is not sparse training, because the goal of dynamic sparse training is to grow the new link without computing the gradient for the missing links, because you want efficiency. The missing links, they don't exist, the knowledge on them, so you should not use the gradient. Otherwise, you do a dense learning, okay? So somehow this method was not a true way to solve the problem. And then I proposed to use epitopological learning growth. It means that you take your topology at a certain epoch n, and you have an oracle that tells you which link should come out. And the oracle is not uniformly at random, but uses some knowledge of the network. And the logical network, in my case, was the Cannistraci theory, but you can plug in whatever you want. You are not obliged. The important concept is they use just the topology you have to grow new topology. So my method was working in this way. You start as normal with a connectivity that is sparse. You remove the link that are less informative according to any type of principle you want. Can be the absolute weight, or can be the relevance, and normalize the way to look at the weight. Then you remove the node that get excluded in the network if this happens, because this is important to be done to eventually verify if the network is self-organized to be smaller. And then you add your new link in the same amount to the one you removed using the link prediction rule I showed before. So this is the first true epitopological learning method. They use only the knowledge of the network and not even the weights. So it means that when I compute the score of the new links, the missing links, I use just the network topology, and locally, I look at the local network. So let's start to see some results. These are the first test we did comparing the performance on toy dataset of MNIST, CIFAR, and so on an MLP with 1% sparsity, okay? And here we show that in comparison to the grow that is random, that is the black, we have two types of characteristics. Either we perform the same or much better, or we anticipate, we are much faster in the process to learn. This it means that the oracle is suggesting the right link to add in advance, okay? And this is crucial because it was the first evidence you have an advantage. But most importantly, and this probably is one of the crucial moments of this talk in which I want to attract your attention, the job I made on network geometry returned back to me. I could use this for explainability because one of the most important things is now to explain why we can perform better and to what kind of connectivity this is related. So what we did is to embed the network in the hyperbolic space and check whether there is an hyperbolic structure. If you have an hyperbolic structure, it means you have that the radial coordinate in the hyperbolic space are related in this type of embedding with the degree of the node. The node with higher hierarchy, they go to the center because they have a higher level of connectivity. They are more important. The one with less go to periphery. So the network is an MLP with initially 1% of link and remain always 1%. And if you grow at random, at the end, you notice that this network, when it's embedded, is similar to the beginning. There is no any particular power law exponent of the degree distribution in the network. So there is no any node that has a hub centering power in comparison to others. Instead, if we embed the network learned using the methodology that I showed, that differ only for the way we grow the link, we notice that there is an hyperbolic geometry in the network with some nodes in the layer in the middle that are crucial with higher connectivity than others. They are the one that reduce the path distance from input to output to performance and time of operation. And interestingly, this is equivalent to gain a meta depth in the network. Why meta depth? Because you need to imagine that these nodes are really projected here, but they are on the paraboloid. So the nodes that are in the center are deeper than others. And this it means they have a higher degree, they have more importance. So it's like there is one depth that is the one of the layer. The other depth is the fact that some of these nodes are more important, that they go out from this plane here in direction of a depth that is related with the relevance they have to perform the nonlinear integration inside the MLP. But not only, we notice that at the end of the training, the network is in general 30% or less of nodes. So some nodes go away. You learn a topology also by removing nodes without any parameter. The self-organization excludes the nodes. And the inner layer arrives to around 18% of the nodes. But again, when we look at the things in a static way, we don't respect the idea of network. The idea of network is to look at the dynamics. So let's now try to look at these dynamics. And so we created a video in which we try to look what is happening from when we start to when we arrive to 100 epochs during the training, how the self-organization of the network is reflected in the geometrical space. They explain the latent variable. So this video is very important because you can understand across the epochs if there are phase transition that bring the performance possibly to improve, how the network organized, is the hierarchy an important factor that start at the beginning. Let's try to see if the video starts. Yeah. So first of all, you see that at the beginning, the hierarchy emerge in the other case of random norm in our way. And then there is a phase transition. Practically, you have that the network pass from a disorder of angular coordinate here. In this moment, the angular coordinate, the colors are not associated with the right layers, so there is that. And the performance, as you see at the beginning, is similar. We are at the beginning of the train, but already the hierarchy, the power law degree distribution emerge in the network at the beginning. So it's a condition very important. They then change the rest of the evolution. And then still at the beginning, the performance is similar, but at a certain moment, flip. And still At this point, what is happening after the fitting is a bit higher here, the red, you cannot see, but jump up. We don't have any proof that there is causality of this phase transition with improvement in performance, but we invite you physicists to try to understand this principle behind the sparse training that is driven by self-organization in network automata. Because if we have evidence that this improvement is associated to the phase transition, and then we are able to generate on purpose the phase transition in neural network, we invent a new way to do training. Okay, completely new, based on the fact that we let jump the performance inducing this phase transition in the system. And therefore, there is a new way to think how to train neural network. Some results in on 1% link. Here we took VG16, GoogleNet, ResNet, different 50, 120, 152. The different symbols means different network. And we apply on them different type of data sets. And we train them with CGT, the method that we developed, the MEST and RIGGEL. They are the method from Google and the other method from the group that developed the set, the method. And the 0-0 means dense network. So independently from all the data set and architecture, if a network perform as a dense, would have a 0-0 improvement, right? So now you see that all the model, dependently from the data set, modified with our training, going into sparse advantage. It means that they go in this upper part, where you have higher accuracy, higher training speed than the fully connected. Instead, RIGGEL and MEST, the method developed by Google and the group of SET, they don't go stable in ultrasparse. So we have the first evidence that we can generate ultra-sparse advantage. It means that we modify the network, we put a sparsity that is equivalent to 1%, we are able to perform better than dense connected network in a very consistent way. And not only, we show that the number of neurons in our case, this is the initial number of neurons, this is the final. In our case, the number of final neurons are reduced to around 30% of the total in many cases. There are some cases in which this doesn't happen, but in many cases it happens. And on real running time, we have an improvement in running time in comparison to RIGGEL. Pay attention that here the scale is log 10. So the improvement is relevant. It's not just the one you see here, it's on log 10 scale, okay? So all of this is in the first article on SCLR. Then we start to do a bit of engineering. First of all, if your method is based on the network topology, at the beginning of the training, the network topology has a lot of noise inside. It means that their link, they still are not correctly explaining the information associated with the task. Therefore, at the beginning, if you take the top predicted link, you might trust a topology that is noised. So we introduced what we call CGT-S, where S stands for sampling, where we sample in a way that is proportional to the link scores. This it means that we create a scheduler also. At the beginning, when the network is noised, you sample proportionally to the scores. So you have a soft approach. Once the evolution go forward, the network will become more stable, and you can trust the topology, you sample with a more rigid approach. It means you just trust perfectly the top score of the link. In the other case, you sample from the top score. And we show that the performance increases significantly. Then we do a lot of study on how to initialize the network, not anymore with erdosorenium, but with a bipartite receptive field network model that we invent in this article, similar to the receptive field in brain network. And then we work on how to implement also the removal in a way that is soft and not only rigid. Anyway, there are many different types of improvements to the point that we give evidence on transformers for machine translation or multi-K as well, so on, we perform better than fully connected at 95% sparsity in some of the tasks, while in others we are very close. And interestingly, we also test on large language model, and in particular, we are the first in this moment in literature to perform better than fully connected on large language model 1 billion. We have a perplexity, the lower the better. There is better than fully connected, while other method previously existing could not. All of this is in the second article, in which we translate all this methodology to transformer and large. Now, why only 1% of link in some cases offer performance better than fully connected? Do you have any clue? Majority of the people in computer science, when I give a talk, told me, oh, but this is impossible. Dense network should work better than sparse. But what? It's not right. You don't know. You don't have a theory that explains the way the task difficulty of a problem and the giving data and problem. We don't have a theory of how to map the task difficulty to the number of parameters. So we don't have a proof that the more parameter you have, the better it is. It's not true. Actually, I give an evidence of the opposite. Not really a proof, but an evidence of the opposite. So any clue why? Correct. We give you the math.
You try to reduce the number of parameters, then you end up with a model that can abstract things, and then probably it's better at generalization.
Correct.
Right? Occam's razor kind of logic.
Yeah. Practically, there is the gradient search in a easier and reduced dynamically, explode the volume. I stress dynamically because what you need to catch is that when you perform a L1 or L2 type of regularization on the loss, you start dense. So you don't learn a connectivity. You learn a weight sparsity, but not a connectivity. But if you start sparse, you apply method of network science to grow the connectivity given the connectivity you have. You are trying to train your connectivity. It's completely different, okay? You are doing really a training of the connectivity. So you are training your network to have a connectivity that is associated to the task from the beginning. So you start sparse, you finish sparse. So this is a completely different, okay? And because of this, the gradient is already moving in a smaller space. Each epochs change the dimension, change the features. Change the dimension that you use. Changing the dimension, it means that you give a big help to the gradient to go towards the new model. Because you cut off, you grow new doors to go down your solution. Okay? So this is indeed a method that opened the way to do optimization in a different way. And pay attention, we should find the intrinsic complexity of the task, problem plus that. So we should search more on these problems because there is a limit due to the fact that the data and the task change the level of parameter you need. Okay, and still these things are not very clear. And my dream is to go towards automatic neural architecture design. My dream is to create a method of a network science AI that automatically find a optimal architecture of number of layers, number of nodes, and the connectivity structure. Like a machine that automatically adapts and learns some shape during the evolution. Not only the weights, but especially how to connect. And now, I suggest you to read this article of Tommaso Poggio. There is a recent speak of an article they made 20 or 30 years before, in which he wrote just some months ago a perspective, sparse compositionality, efficiently computable intelligence. Is actually on this topic of sparse neural network. And he sustained that with some article he published before, he could give evidence that sparse neural network, deep neural network can learn some function, they are even better than advanced one. So practically, there are also evidence of other authors that this could be possible. The fact that it was not done before doesn't mean anything, because now with the new study I am doing, I support the theory of Tommaso Poggio. They didn't really create the algorithm, but create some formalism, some demonstration, giving evidence that this could be possible. And today we have the evidence that indeed this is possible, at least with this new work done. And also you can find this article on OpenAI. Pay attention, here is still weight sparsity. So they work on trying to find the circuits that are interpretable. It's true. If you have a less parameter, you have a shape of, they explain the connectivity inside your type of network, you can explain better what is the circuit they are associated to some type of. Now there is a new article in CLR. We give evidence that in implementing this method in spiking neural network that are ultra sparse, we can have strong improvement at the level of energy consumption. This is a log scale, so 0.89 on a log scale is 99 on a log scale is really low. Okay, so here we have evidence that we reduce significantly the energy consumption. So once we create now spiking neural network, we put inside the robot, they work in this way, we reduce significantly the impact of energy in comparison to use a normal circuit. So now neuromorphic computing is using also this approach based on Cannistraci, and this was published in ICLR 2006. Is a collaboration with a integrated circuit professor in Tsinghua. They saw my talk, came to me and told me, listen, I have a problem. If the spiking neural network are not ultra sparse, I don't have an advantage in the chip. Can we use your method? I say, yes, let's try, let's see how it's going. And now they're building the chip, the hardware based on this one to let the robot, different type of edge computing work in this way. And the evidence are of big advantage at the level of energy consumption. So in conclusion, after around 20 years, I was able to reply to the first question. So what about the morphology? But about the morphology, we have a few minutes, and I will tell you that regarding the morphology, we made this article in which we build the first neuromorphic computing hardware, in which we go away from the idea of point neuron model. We really implement the intrinsic integration. So our model is based on the dendrister. We take a transistor, we put a sol gel between the gate and the under part of the drain, the source, and we use this ion channel of the sol gel to emulate the behavior of ion in the membrane. And by means of this one, we create a real dendrister, a tool that works like a dendrite. And then we create a network of this one. And here we show the single branch. This is a dendrister, works similar to a real dendrite in biology, that we can find the direction selectivity. If a signal going one direction, in the other direction, we are able to detect the difference. You see, in direction is giving a higher level burst, and the out direction is giving a lower, because you integrate here in a way that you sum up towards the opposite. And then I propose the idea to implement also silent synapses. There are synapses that activate only once the synapse is before activated. This improves the detection. Then using this principle, we create a simple circuit that can detect the input and output by using an inhibition synapses here. If you go in one direction, this synapses is not activated, this inhibition is not activated, and you activate also only this dendrite, this neuron. If you go in the other direction, this is activated because you feel the one before, you activate the inhibition, and you detect the indirection. By means of this one, we could extend with ramification on a retina, and with radial assembling, you can replicate the same behavior to find the depth. And we were able to emulate the fly of a symbol of a butterfly. This is not a real butterfly, but the idea is that moving 3D. It's like a butterfly that moves in 3D, but doesn't move the wings, because it would be a bit more complicated. And this is what you would see in 2D, in the rain projected on the retina. And using this device, we actually can, in a neuromorphic way, compute the vectors of the movement in 3D. So emulate the visual perception. When Tommaso Poggio saw this one, he was really shocked because he worked a lot on this concept on neural network for years. And now we implement this in reality on directly on a dendrist or a emulation of the dendrite. It was really interesting. And the article also, now we are going to show that behind this checkpoint, there are actually hyperbolic geometry. So I'm trying to push the idea of network neuromorphic computing and predict in advance, looking at the network, the behavior of the nodes in the network. And I want to thank all the co-authors for this article. There is published in 2024. And this is a new article. It's actually a comment on how to, on the next generation artificial neural network that will come. We discuss what we envision of it. So thank you so much. If you are interested in this work, you can find that these are the articles related with the dynamic sparse training. You can take a picture of this page and then look at them. There are new articles in ICLR that I can comment now. On neuromorphic computing, there are this article. And for anything, you can contact him on my email, and we'll be happy to reply to your questions.
All right, thank you, Carlo. And yeah, we open the room for questions. Let's start from here.
Thanks for the talk. You mentioned just a little bit about how you decide which of the connections to remove, and you said that you could do it just based on small weights, but you had some other schemes.
Yes,
wondering, for the results that you showed, is just the naive thing of removing small weights typically sufficient, or do you often have to do something more subtle?
Yeah, so we explored also the fact that you could look at the relevance of a link. It means how relevant is a link in comparison to the neighbors. But we discovered that in general, the rule of removing the links with the smallest absolute weight works quite well, as the previous colleague generally used. So at the level of removal, for the moment, majority of the tests we do are all based on removing the links with the smaller weights. However, what we introduced is the fact that actually I don't show here, but inside the article we do a lot of tests to investigate the extent to which, instead of a rigid removal, a soft removal, the sample with the weight is useful, and which moment of the training is useful, and in reality, in which kind of problems is more useful or not. So what we notice is that the thing that is more important is to understand when you need to do a soft removal and when you can go for a rigid removal. And this, of course, is at the beginning, because at the beginning, the weights are not really good approximations, and the topology also. So the beginning is much better to go with a soft removal. It means a removal, the sample according to the scores or according to the weights. It depends if you do limb prediction or you do removal. And then slowly you do a scheduler. You converge towards a approach that is more rigid, because the topology and the weight start to be associated to the task in a more robust way, so you can trust them, so you can be more you can go for rigid removal. Yeah.
More questions?
Yeah, I was just curious, how do you decide when you initialize how sparse to start the network? Is it just like a trial and error, or is there some theory behind that?
There is no theory. So what do we do? There is no theory because really the real theory should be the one that help us to understand, giving a task, so problem, question, plus data, what is a possible range on intrinsic sparsity that the problem is. So what we do is this one. That's why we need to spend a lot of money, because it's pre-training, unfortunately. So we need to do tests in which we test a different level of sparsity. Generally, we start from 70% because we want to go on sparsity. Okay, if you go 50%, it's already too dense. This is more interesting for NM, semi-structural sparsity for GPU and NVIDIA. We also now have an article in which we show that we can use a 50% sparsity of GPU and NVIDIA. So we have this article here. This and then semi-structural sparsity, where we show that 50% we perform better the method based on L1, L2 to create a semi-structural sparsity. But the true important topic for physicists, in my opinion, is to understand the sparsity when you go lower than 70%. And then what we do is to test 70, 80, 90, 95, 99, and so on, and show how change the performance in this method. Because of course you cannot just put up the value. You want to understand what is happening when you reduce the sparsity in general. And to convince the reviewer, I think this is right. I do myself. So I spend a lot of money to give it to my reviewer something that is interesting. I don't want to get there and just say I put up this one. It's not right for me. So we spend a lot in this, in giving the profile of the performance change with sparsity. Also because it's very interesting, it depends from the task, right? And then somehow if you had a lot of, if it didn't cost too much, we could do many tests and try to find the rule, no? In this way, practically data-driven rule, we could try to do, analyze all this pattern and find data-driven rule. And this would be probably a project that could emerge in the moment that the sparse chip are more available. For the moment, only Cerebras has sparse chip in the world. So pre-training sparse is a bit difficult, it costs a lot of money because it costs equivalent to a dense on normal GPU. On chip, they are particularly designed, of course, is extremely fast. On CPU is faster.
Are there any toy problems where people have made progress there, where they understand why a certain amount of sparsity is optimal, or is it just totally
no, in this moment there are not, but I totally agree with you. In fact, that's why I'm here. I wish to motivate you guys to look at my video. There is based on a toy model, but pay attention, is not the ground truth. Because when you have a ground truth, you really know what you infused inside the data, so you can really make sense perfectly. That is a minist. You can do all these minist data set, whatever you want, because they are small. And anyways, consider a toy model, although it's not, because for me, a toy model is the one that you generate, you know what to put inside, okay? But it's considered a toy model because it's basically, we know a lot on the data they are in minist, the way they are generated, the fact that they are on a manifold and so on. So you can try to already look at the video if you have any idea of collaboration or study. I'm here for this reason, because in computer science, the people are in this moment in Tsinghua just focused on getting higher performance and less and more efficiently in transformer and large language models. Instead, my point of view is that we need to start to understand how the things work. Yeah.
Would you comment on how making the entire network sparse versus using a mixture of expert kind of architecture where certain region gets highlighted when you are depending on the task, instead of making the whole network sparse, you have some sort of a router which excites certain region, and that could also be an efficient way of compute. So I wanted to know what's your thought?
Yeah, I totally agree with you. The mixture of expert is absolutely a correct way, but what we want to investigate, and now we are doing to make sense of what is here, is to verify whether during training, in a contextual way, so contextual training in the sense that is related with the input, we identify that this sparse network is activated in special model. So practically, we want to investigate the extent to which this the community organization that emerged during the training has inside a other community organization that is related with the context, with the samples. So that samples, they are similar, activate some paths, a circuit in the network, other activate others. If we succeeded to give evidence that this is actually happening in this sparse network, and we have some initial evidence also in the epitopological learning article. In this first article, we analyzed some imaging data set that the pattern they are selected by the sparsity. Then we can start to think whether, in reality, behind this sparsity of the topology is masked also a sort of a mixture of expert structure that is activated when the token enter or when the the pixel of the image. Okay, so the question is this one. Is there a nested hierarchy inside this sparsity that we have that is activation related? Yeah, this can be done, and is the next step. But you know, before I did this evidence, there was nothing in this way. So now it's opening the way. You might call these tests. Yeah, I agree with you.
More questions? I have one actually. So you mentioned now the experiments or like applications to neuromorphic computing of this approach in the last.
Yeah,
couple of slides.
this is in this article on spiking neural net.
Yeah. So my question is more broadly, what would be the right hardware for a network that is built and trained according to this sparsity principle? Like,
Yeah.
Would it be these neuromorphic computing? Would it be something else? Would it be GPUs? Have you thought about?
Yes. So in my opinion, the algorithm hardware co-design is related with the type of application that you want. I'll give you an example. If you use this spiking neural network, it means that you do the chip, they are analogic, and you use also activation sparsity. So this article is very interesting because in this spiking neural network, you see this is the firing rate. We give evidence that the sparse network reduces significantly also the firing rate. But the firing rate is related with activation sparsity. So here we have a bigger advantage over reduction at the level of energy consumption. So the reply to you is very useful in the moment that the sparsity that is in connectivity trigger also a reduction in dynamic sparsity of the signal. And this is actually evident in this case. So the spiking neural network is an emblematic example where the structural sparsity increase also the activation sparsity because you have a reduction in free rate and keep the performance. This is fully connected. This is the 99% actually on different type of data sets. We show that we can perform similar or even better than the fully connected initially. So this is show that this type of architecture are very useful. Another one, but these are easy to implement on a chip. Another one that would be interested are memory store cross-bar array. But the memory store cross-bar array in this moment are lattice created. So I don't know if many of you investigated the memory store cross-bar array. They are very interesting. They use the idea that just the idea, the normal Ohm law. So you give an input current, and then you measure a difference of potential. You do this on a bar array, so you can implement matrix multiplication in one shot, or it costs O1. Okay, it's very interesting, probably the technology of the future. But the problem is there, how we can create the nonlinear sparsity that we have in this network in cross-bar array is difficult. Okay, so there is start to be a problem. So in conclusion, the right hardware is the one in which the structural sparsity give evidence of activation sparsity gain, like the spiking neural network, this one. But attention, this happens if you are ultra sparse. So it's very important to stay very low in number of units. And that's why our method was useful for this application. And then this can be very useful on edge computing, robot device that move drones, all these kind of things.
Thanks. Any more questions in the room? Or question online? We don't have. So if we don't have any more, we thanks once again, Carlo, for the wonderful talk.
Yeah, thank you all of you. Thank you for this invitation.
And as usual, we move our reception upstairs.